Can you all see my screen? Okay, good. All right, good. Right, so like I said, we want to talk about the electromagnetic spectrum. That's to me the most important thing that we want to talk about right now. And I just want to make sure you understand all the 5 parts that you are needed to know for this for IGCSE. So I'm going to check. Let me make sure that I'm sharing my screen. If you can't see, you tell me, okay? Right. Can you all hear me? Can you see the screen? Good. So everybody, this is the chapter of waves, and in the chapter of waves, you need to know about light and you need to know about sound. So we are studying light. Light has a lot of things, or it has 3 big things, or we can say 4 big things. There are 4 big things that you must know for you to say you're good at light. You must know ray diagrams. You must know about refraction of light. You must know the electromagnetic spectrum. Then you must know dispersion of light. So when you are dealing with this, remember we said that waves, you need to know general properties. Yes. Oh, okay. Make sure you are watching the phone so that when I put it in the group, you can see it. When you are dealing with waves, you need to know general properties of waves. Then you need to know about light. Then you need to know about sound. And when you need to know about light, you need to know about refraction. You need to know about refraction. Then you need to know electromagnetic spectrum. Then you need to know about ray diagrams. Then you need to know about dispersion of light. You need to know about dispersion of light. So we are looking at one aspect. Yes. Physics. So, and then you need to know about light. So our focus is on electromagnetic spectrum, one aspect of light. I want you to know what we are doing. We are doing this portion here. That's the portion we're doing right now. So let's go through it and let's make sure we know it. Have you seen? This is your chapter 3, waves. Have you seen it? We already did the general properties of waves. We understood what is a transverse wave, what's a longitudinal wave, what is wavelength, what is frequency, what is amplitude. We talked about those things. Now we are looking at light and we're looking at electromagnetic spectrum. We're looking more at it. We want to see more. So when you do electromagnetic spectrum, which is what we are looking at today, you need to know that this is this, should I say chapter? Okay, you can say this chapter. We're looking at it, you can say this chapter of electromagnetic spectrum. Okay, of the electromagnetic spectrum is broken down into 5 parts. Is broken down into 5 parts. Okay? 1, you need to know about electromagnetic waves. You need to know about electromagnetic waves. Then 2, you need to know to say, okay, what the definitions? The definitions, electromagnetic waves, and their types, and the 7 types. You should know, and the 7 types. Just to know what is an electromagnetic wave, what is the property that they all share, what do they all have in common, right? You must know about them. Then you need to do the second thing, which is you must know the uses of electromagnetic waves. And I'm going to give you the summarized version, then we'll look at the expanded version. But you should know the uses of electromagnetic waves. Then you should know the dangers of electromagnetic waves. Okay? Dangers of electromagnetic waves. The dangers of electromagnetic waves. You must know. Then, when you know the dangers, you must know about electromagnetic waves being used in communication. Okay? Communication. In other words, the use of electromagnetic waves. Right? Then, finally, we are going to look at the last part, which the syllabus wants you to know under this, is digital versus analog signals. Okay? Digital versus analog signals. Have you seen, class? So let's talk about the summarized version of all these things. What are the key concepts of all these things? So summarized versions. We can look about them in detail. But let's do it right now. Summarized version. You have, write summarized version. Then you put part 1. Okay? Part 1, electromagnetic waves. Electromagnetic waves. I just want to make you know the most important concepts about each idea. Are we together? Right. What are electromagnetic waves? So I want you to write here to say let me just switch on the aircon. Okay, I want you to say electromagnetic waves. Write with me. I'm going to give you a lot of important information here. Just write to me to say electromagnetic waves are transverse waves, because they are light waves, right? Transverse waves that transfer energy to an observer. Okay? From a source. From a source. So electromagnetic waves are what, class? Electromagnetic waves are transverse waves. Again, are we together? Now write with me to say, there's a lot of information I just want to give you so you just know. All electromagnetic waves travel, write with me, travel at the same speed in a vacuum. Okay? Travel at the same speed. And what is it? Or travel at the same speed. Say in a vacuum. And the speed is 3.0 times 10 to the power of 8 meters per second. Which is the speed of what? Speed of light. This happens to be the speed of light in a vacuum. Okay? All electromagnetic waves travel at the same speed, because electromagnetic waves are types of light. These are the different types of light. Although we cannot detect some of them, we can only detect one part. But it doesn't mean the others are not there. They are there, but we cannot detect them with our eyes. So, but they are there, these electromagnetic waves. So, let's put here order of electromagnetic spectrum. Let's see the order. There are a lot of things that I'm going to be talking about, but here, this is the last part I'm talking about on the first, then we go to the second idea. We say Army Vuxi. Army Vuxi. So here, can you see, these are radio waves. Then here we have microwaves. Then we have infrared. Then I want you to say this is going to be visible light. Is there anyone with a question? Yes, did somebody call my name? Oh, you what is it like? You can't see nicely. Is it better? Okay, good. Can you all see my screen? Look at this list, because from here we want to talk about the uses, the dangers, then we talk about communication and stuff. So what I want you to see is, okay, here, visible light, then ultraviolet. We're talking about the electromagnetic spectrum itself. This is X-ray, then this is gamma ray. Can you put here? This is gamma rays. Yes, I heard somebody saying go up. Yes, you can ask me the question. It's a little bit different from what we did last time. Yes, here this was a 1 minute recap. Okay, this was a 1 minute recap of the things, but it's not going to be the same. It's not going to be the same. I'm not repeating. Okay? Can you all hear me? Okay, good. So, yes, this is the electromagnetic spectrum. Now, what do we say here? What do we say? I want you to say this one has highest wavelength. Okay? Radio waves have the highest wavelength or largest wavelength. But here, this has the highest frequency. Okay? This one has the lowest frequency. Okay? Then this will have the smallest wavelength. Have you put? So highest frequency, this also means highest energy. Can somebody write for me, please? So have you seen Army Vuxi? Have you seen Army Vuxi class? Hello, everybody? Have you seen Army Vuxi? Antonisha? Good. Now let's go to part 2 now. And I'm giving you everything as tables. Just tables. Put it to say uses of electro uses of electromagnetic magnetic write that, uses of electromagnetic waves. Okay, and here I want you to say the wave. Here we'll say the wave, then here we'll say the use. This is the summarized version. Now, here for use, I want you to say main use. Start with radio. Main uses, I want you to say broadcasting. We'll talk about it again later. Broadcasting, and I want you to say on radio and on TV. Now, we'll go to the next thing. Microwaves. Then we go to the next thing. Infrared. Microwaves are used for mobile phones. Microwaves are used to cook. Did you write that? To say microwaves are used for mobile phones? And can you write for me to say Wi-Fi? Okay, these are three important uses. Can you see the use of microwaves, class? Hello? Let's keep going. These are the use of microwaves. Then, okay, so it's not used for broadcasting, but radio waves are used for broadcasting. Infrared is used for remote controls, and it's used for thermal imaging. Here, put it for me to say thermal imaging for infrared, remote control. Then visible lights. On visible light, I want to see you write this. It's used for lighting, okay? Did you put on visible lights? Did you put on visible lights? I need you to know this. These questions do come. Radio wave is used for broadcasting and TV. Microwaves are used for mobile phones. Microwaves are used for Wi-Fi. Wow, really? Microwaves are used for satellite communication as well. I should put that to say satellites. So here, infrared, nothing to do with Wi-Fi or what. It's for remotes. And visible light is for photography and all these other things. Then now we are going to ultraviolet. And these, so let me say, the ones that come after visible light, they have such high frequency, high energy. Remember, our frequency or the energy of each of these waves, how dangerous they are, it increases as you go down the group. It increases as you go down the table. Are we together, class? The waves at the top have very small energy, very little energy. Radio waves are not dangerous. We can't fear radio waves. You've never heard anyone say fear radio waves. Microwaves, a little bit dangerous. It gets dangerous as you go down. So now, for ultraviolet, these are powerful. So their uses are also powerful. So I want to see from ultraviolet going down, I want to see that you remember that the uses are big, because these are powerful ones now. This is used for sterilizing. This is ultraviolet is used for sterilizing. Okay? It's also used to detect fake notes. Okay? Are you ready? These are uses of microwaves. Then we go down to X-rays. They are not used to sterilize. Yes. Yes, they are used to detect fake notes. There's something put in original notes, which when you take a fake note and you work with an ultraviolet ray, you go through it, you see, this is not original. Even, I mean, the ultraviolet from the sun, if you go to a person and you are buying in a shop, have you ever seen them lift, then point it up towards the sun? Do you know UV light comes from the sun also? What do you see when you take an original note and you face it up, you make it, you look at it through the sun? Okay, if you see a watermark, there's something which they call a watermark. There will be something inside that note. If it's a plain fake note, if it's a fake note, then it will be just a paper. The ordinary paper, when you lift it up towards the sun and you try to look at the sun through it, you're gonna see nothing. Then you know, wait, this is something fake. Okay? Because UV light comes from the sun. You know that, right? It also comes from the sun, all right. So ultraviolet for sterilizing and for detecting fake notes and for all these other things. Now let's go for X-ray. X-ray is used for medicinal purposes, okay? So for medical imaging, you learn medical imaging when you do, for those who are going to do A-level physics. Then security scanning. Are we together? Can you write this? Write it as fast as you can. We use X-rays for this, for medical imaging and for security scanning. Okay? Write this, write this, write this. Right, now let's go to the next one, eh? Have you written this? Class? All right. So, by the way, yes, write fast. When we say security scanning, have you ever, when you're at the airport, they will make your bag pass through those scanners, right? They are trying to detect if you have narcotics, which are like drugs, if you have explosives, bombs, or if you have hidden weapons in your bags. You can't hide, my friend. When we take an X-ray and we screen that or we inspect it, we're gonna be able to see there are metal objects here. We'll be able to see the shape of the gun nicely in there. Are we together? To say, there is a gun there. Are we together, everybody? People? Yes. So there's another use of X-rays. There's another use of X-rays. X-rays are also used for medical imaging. Now let's go. And security scanning. What's the other thing? Gamma rays. These ones are deadly. You don't want to be just exposed to gamma rays. Gamma rays, yes, they are used for cancer treatment. Don't tell me we use X-rays. No, we use gamma rays. For cancer treatment and for also sterilizing as well. Cancer treatment and for sterilizing. So this table should become your best friend. Are we together? It has important uses of electromagnetic waves. Okay? Here, radio and TV, it's for radio waves. Radio waves. They are used for broadcasting. Microwaves are used for cooking, for Wi-Fi, for mobile networks. Infrared is used for remote controls. Have you seen this? So you know that remotes have that red light in front of them. Have you ever looked at the remote control? Students? Yes. That's an infrared ray. That's an infrared ray there. Okay? All right. So now, let's go to the other things. What did we say? Okay, we said we have another use for infrared, which is thermal imaging. If you say thermal imaging, it's just you use heat. You look for you use heat to see an image. By using heat, just know that. You look it's like infrared radiation is detected, and then it will be converted to something that your eye can see. Okay? Your eyes wouldn't be able to see it, but this thing, infrared radiation is detected, and then they convert it to be for you to be able to see anytime, even at night. So lightning. Okay, no, for visible light is lighting. For vision means for you to see. For you to see, yeah. For you to see. Then for photography as well. But then for lighting. Then we have ultraviolet for sterilizing. You should now know all these. You must write this table on your own without looking. That's the best way to memorize it. You put it away, then you start writing it on your own. Writing these uses. Are we together, students? Make sure you know this in case they ask you about them. Are we together? Now let's look at the third part. We said we want to do 5. The third part, let's talk about dangers of electromagnetic waves. Let's talk about it. Dangers of electromagnetic waves. Dangers of electromagnetic waves. So, the frequency of electromagnetic waves yes, that's why we say microwaves are also used for cooking, huh? Yes, microwaves have, yes. That light in microwaves is actually, you'd be having microwave rays. Yes, that's very true. So, let's keep going. The frequency of, well, good. I like that. The frequency of electromagnetic waves, is directly proportional. Let me write that. Is directly proportional to the energy. The frequency of electromagnetic waves is directly proportional to the energy of the wave. Okay? As the frequency increases from radio waves to, as the frequency increases, we are writing, as the frequency increases from radio waves to gamma rays, the energy increases. So gamma rays have high energy? Yes. So are they dangerous? Yes, that's why we are talking about dangers. So they are dangerous, watch out. The last three types of electromagnetic waves, which on your army Vuxi, it's going to be ultraviolet, X-ray, okay? Ultraviolet, X-ray, and gamma ray. These three, ultraviolet, X-ray, and gamma ray. Can you see them? Can you see ultraviolet, X-ray, and gamma ray? Are all high energy waves. They are all high energy waves. And are ionizing, which means they can cause or they can damage the DNA, causing cancer. Are we together? You should know these dangers. So let's write again. Let's write again the Army Vuxi. And we put the dangers of each. So we're going to say wave, then we're going to say the danger. Okay. Yes, I've scrolled up a little bit. The last three types on your list when we write Armvuxi, on the list, the last three types they have high frequency. You should tell people to say, okay, they have a small wavelength, yes, but they have a high frequency. Because when you have a small wavelength, we know that as we go down this electromagnetic spectrum, they now have low energy they now have low wavelengths. Okay, good. As you go down the electromagnetic spectrum, the wavelength actually reduces. But so what, man? We don't care. Okay, the wavelength reduces, but so what? The most important thing is that frequency increases as you go down. So the frequency increases, yes. Are you sure? Yes. So as the frequency increases, what risk does that come with? They have more energy now. The waves that have higher frequency have higher energy, which makes them dangerous. Because if they have high energy, what does it mean if they have high energy? It means they are ionizing. So what do you mean by that? What do you mean that by they are ionizing? They are going to give energy to your cells. And when a cell gets energy, it mutates. So, your cell gets energy, it will mutate. We'll talk about mutation when we talk about variation and selection. The next chapter in biology, after inheritance, the one we are doing right now is inheritance. We'll see what mutation does. It produces new things that your body didn't know. It produces new alleles. And those ones, they're going to make new things be made by your body. And that's a cancer, my friend. That's cancer. Foreign things now growing in your body. So you don't want your cells getting energy. You don't want your cells absorbing energy. So these waves are deadly because they can give my cells energy. And if my cells get energy, they can mutate. They can damage the DNA. And this causes cancer. So we don't want high energy waves because they are ionizing, and this leads to them damaging the DNA, which causes cancer. So now let's write each of the waves and their dangers. Let's see the dangerous ones. We've seen their uses. Thank you for telling us their uses. We want to see their dangers also. Why should we only know about the good of these waves? We want to know about the bad as well. The good, the bad, and the ugly. So now let's write R me vuxi. So it's R me vuxi. So I want you to know that you say R me vuxi. Then you say X. Then you say gamma. That's the R me vuxi. This one is gamma. What is R? Radio waves. What is M? Microwaves. What is I? Infrared. What's V? Visible light. This is the region that we can see. This is the only region that the human eye can detect. Then U is ultraviolet. Then X is for X-ray. Then this is for gamma ray. Oh, serious? Yes. Dangers of electricity, dangers of electromagnetic waves. Let's see them. Radio waves, of course, these ones have very low energy. So, because they have very low energy, we know that they are not dangerous. Because we know that dangerous ones are there as they get more frequency. That means they're going to have more energy. That means they're going to be more dangerous. As you go down, these last three are the cancerous ones. Hey, these ones, we have to write cancer before we even get there. We can write skin, cancer, then here, cancer, then here, cancer. Write that before we even get there. Yes. The last three. No, I'm saying they are dangerous. If exposed, if you are exposed to them, you can get cancer. Yes, it causes ionization of cells, which just means it causes the cells to get energy which they didn't have. So these cells get energy, then they change, they mutate, and now you have a cancer. Your DNA is damaged. You now have fake new stuff, and then now that's a cancer because new things will be coming up in your body. You start having things growing in your body. Yes, the higher the frequency, the lower the wavelength, but the more dangerous the wave. When frequency is high, the wave is dangerous. Why? Because they have high energy. Yes. What are the dangers of things like microwave? Microwave, we saw it last time that it just causes internal heating of your organs. Internal heating. Here, internal heating of body cells. So it's also bad. Internal heating of body cells, which can cause organ damage. Microwaves, don't play with them. This one, infrared, skin burn. Infrared, the problem is skin burn. Now, visible light, you cannot hurt me because that's the light I used to see every day. So we don't talk about it. No known danger, of course. For this one, it's off. No known danger as well. It doesn't have any danger at all. The light that we used to see. We need it. X-rays, no, let's start with ultraviolet. Ultraviolet, they can also cause eye damage. You can't look at the light from the sun. Eye damage, and it can cause skin cancer. Then X-ray. X-ray, what happens with X-ray? Cell damage. X-ray can damage cells, which is not good as well, because cells are you. Cells are what makes you. So, yes. Pardon? Okay, mutation is not a bad thing. The bad thing is the cancer that comes from the mutation. So I want you to make sure you use this word. This is the word. Okay? You won't make people get scared or make people wake up by telling them that, hey, you have mutation. They'll say, so what? But if you say to them, hey, you have cancer, then they'll wake up. You understand? Gamma ray is so bad. Gamma ray is just so bad. So I want you to say this one. It causes severe cell damage. Isn't you know gamma ray is there in radioactivity, right? Severe cell. Don't you know that? Hello? Gamma rays are part of radiation. We have alpha, we have beta, we have gamma. So gamma is radioactivity. Radiation, you know that it affected Japan for years because of that nuclear weapon. That is why people don't want nuclear weapons. When we say yes, and Nagasaki, yes. Nuclear weapon just means, when you hear the word nuclear, it means energy from the nucleus. There is one thing you must know, everybody, right now, is that the nucleus of an atom, not of a cell. Remember, an atom and a cell are two different things. Don't you ever confuse nucleus of a cell and nucleus of an atom. A cell is much, much bigger than an atom. A cell is made up of atoms. Atoms are small. They are not even alive. A cell is the smallest, is the building block of life. It's alive. A cell is alive. It's much bigger than an atom. You can see a cell through a light microscope. Not an atom. Nobody has seen an atom. What? Nobody has seen an atom? Yes. So how do we know the shape? They predicted it. They are guessing. They did some experiments by firing things inside, and they saw that, when I fire things inside, a lot of them pass through. But when I fire at the center, they hit and bounce back, which means the nucleus is at the center. That's how they discovered an atom, the shape and everything, through firing things in it. But nobody has ever seen an atom inside. If we had seen it, it would be much easier. So an atom is very small. So here we are in physics, we're not in bio. We talk about atoms. Small, small, small thing that even makes the cells. The cells are made of atoms. Now, this atom, when you go inside its nucleus, Albert Einstein told us, it's not us, it's Albert Einstein. We were told by, and many others, that there is energy in here. And he said it is E equal to mc squared. This is a bad formula. It's a powerful one. There is energy inside the nucleus, and energy inside the nucleus is called nuclear energy. And what happens is when energy inside the nucleus comes out, if it comes out, it's deadly. That's what we call radiation. Radiation is when energy, there is a lot of energy inside that small thing. Trust me, guys. Bill Gates was actually trying to build a nuclear power plant. You can go and check it after the lesson to see how far he is with that idea. You can actually give people electricity from the energy that comes from here, and they can cook and do a lot of things. So nuclear energy is energy from this. Is energy from here. It's deadly. It gives cancer and you die. People who were discovering it, a lot of them, they died. A lot of them, the people who were researching on this. Marie Anne Curie, you can go and look for them. And a lot of the people, they sacrifice their life, because once this energy gets into you, that's cancer. And cancer means you have something growing in you which should not be there. And that thing which grows in you will be killing your cells until too many cells are damaged and you are dead. And you can die. So here it is. Gamma ray is part of the three dangerous things that come from here. Alpha, beta, and gamma. So don't think gamma is a friend. It's not a friend. There is no friendship between us and gamma. It causes serious cell damage and it causes cancer. Okay? We have no friendship with this one. Don't have any friendship with gamma. Are we together? Right. Now, let's talk about communications. The fourth thing, communications. We want to see how electromagnetic waves are used in communications. Particularly these ones. The ones that are used for communication. Radio waves, microwaves, infrared. Infrared, they're used remote control, thermal imaging, and for optical and in optical fibers. Okay? Used in optical fibers. So now, let's see in communications. We expect to see about radio waves, we expect to see the microwaves there, and we expect to see infrared there, because these three are used in the communication industry. Let's see in communications. Telecommunications. Those who do that, there is an engineering called telecommunications engineering. It's not an easy one, eh? You can research on it. It's one of the hardest, eh? At university, it was one of those that at the smallest graduation numbers percentage. Ooh, really? Yep. Let's go. Communication involves sending information using electromagnetic waves. Are we together? Sending information using electromagnetic waves. What? Really? Sending information using electromagnetic waves? Yes. Really? Yes. Okay? That's right. Let's start with what? Radio waves. So information is actually sent using electromagnetic waves. Are we together? All this info. You know why? It's because electromagnetic waves are fast. Remember, there are types of light. They move at the speed of light. Okay, can I ask you a question? What happens first? Do you see lightning first, then hear thunder? Or do you hear thunder, bah, 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 then you see lightning later? Lightning first. When you see lightning, you want to run because you know that thunder is coming, right? Now let me tell you something which is nice. Do you know that lightning and thunder happen at the same time? Do you know that? Thunder is the sound that comes with that lightning that you see. So people actually run away from thunder, but the deadly thing is the lightning. Thunder is just the sound which takes time to arrive. Yes, yes. They happen at the same time, but sound is slow. Sound moves slower than light. Yes. Light is amazing. Pardon? Okay, the sound waves move at 550 meters per second. Light moves at 3.0 times 10 to the power 8 meters per second, which means if we convert this to number with zeros, it will be 3, then 1, 2, 3, 4, 5, 6, then 7, 8. So it will be 300 million meters per second. This is the speed of light. This is the speed of sound. So which one will get to us first? Yes, this is the speed of light. Can you see? 3.0 times 10 to the power 8. It's this one. It's this one, right? Then here is the speed of sound. So if they happen together, Roderick, let's say you put two cars on the ground. Okay, you put a rocket which moves at this speed and another rocket which moves at this speed. Then you shoot them. Which one goes up? Which one gets to the destination first? Good. So that's the same thing that happened with lightning. They happen together, but then the light is moving much faster. So it gets here much faster. So the only way that you, Roderick, will be able to hear me is that this wave of sound should be converted to light. It should be converted to a wave. And a wave is a type of light, but it's a type of light that we cannot see, but we can use it. So all those things, satellites, whatever, boosters, all these things, what are they doing? They are moving information as light waves. Because if we try to move it as sound waves, I'll speak right now, then I'll wait for a few seconds for you to hear me. Do you understand? But right now, you are hearing me immediately. Can you imagine? This is how fast you are hearing me. We can actually have a conversation. It's because you are hearing me immediately. It's almost like you are right here with me. Are we together? It's because it's moving at the speed of sound. Information is moving as an electromagnetic wave. That is the secret of communication. So telecommunications, well done, engineers. Well done. By the way, engineering just means doing something which makes life better. That's what they are there for. They should give us electricity. They should design cars for us. They should design stoves for us. They should design light bulbs. They should design things that make life easier. You understand? So communications is a part of engineering. They make us hear one another and talk to one another from anywhere. Are we together? So, what is communications? It is sending information using electromagnetic waves. So let's see how radio waves are used in communication. Are you hearing me, class? Well done. Let's see what is the strength of radio waves and where are they used. Here I want you to say radio waves are used in local broadcasting. They are used in local broadcasting. Do you know the reason? The reason is because they diffract. Okay? Reason, you need to know the reason. Use and reason. Reason, used in communications is because you should know this region. They diffract around objects. Let me explain something to people. So there is a secret. When we say the word diffraction, it means a wave is spreading. Look at what happens. Let's see, a wave comes like this. It's going straight, isn't it? This is a wave. It's going straight like this. Then it gets to something which is like this, a door or an opening. So what they say if this opening, sometimes it's called an aperture or an opening. You do more about this at A-level physics, those who do A-level physics. This is your wave nicely coming. If this opening here is the same size as the wavelength, because this is the wavelength. Remember, this is wavefronts. This is wavelength from one wave to another. If this opening is the same size, then this thing will really diffract. It will really spread nicely and go everywhere. Have you ever seen this type of drawing around radio waves, sound waves, to show that they are diffracting? They'll be diffracting, which means spreading everywhere. So for a radio wave for a wave to really spread everywhere or to diffract, it needs to have the same wavelength as the opening. So we all know that radio waves, these ones, they have the smallest, they have the shortest frequency, but they have the largest wavelength. They have the largest wavelength. So because they have the largest wavelength, when you move them, when you push them through mountains and buildings, the wavelength of a radio wave is almost the same as the distance between buildings and mountains and stuff. So guess what? It will be diffracting nicely. Radio wave will be spreading everywhere nicely, because when it passes through these things, mountains and things, and it spreads more and more. And when you lift up your aerial, it can get the signal that is coming, because this wave has been spread all over. So for local broadcasting, you use radio waves because they spread around. They diffract around objects. Are we together? You don't need to help them. They'll do it on their own. They spread on their own when you push them through buildings and all these things. Are we together? Yes. So they are used in local broadcasting, radio waves. Now let's do microwaves, which we saw, that are used for Wi-Fi. Yeah. Microwaves. Starlink. Yeah. Thank you. Microwaves. They are used in mobile phones, Wi-Fi. Wi-Fi is spelled like this. Wi-Fi. And satellites. Really? So satellite communication, yes. So the communication NASA was doing, yes, when they went to the moon, yes, was microwaves, yes. Wow, really? Yes. Why? Why do they use it? Used in mobile phones, Wi-Fi, and in satellites. Why? Because reason is they can pass through the atmosphere and they can travel long distances, okay? They can travel long distances. So the Wi-Fi connection router to my phone is a microwave, yes. They travel long distances and can move through the atmosphere. Are we together? Hello? Well done. So can you see how important these discoveries that people did were? They changed our lives to discover this electromagnetic spectrum and see that all of them are types of light. They move fast. That was a big thing. A lot of people had been dedicated to this. That's what you must do. Be dedicated. You'll get to this level. Then number 3, infrared. Okay? Infrared. I want you to say here, or visible light sometimes. Or the normal light, or visible light. Okay? Used in optical fibers. Right with me. Used in optical fibers. Used in optical fibers. I told you yesterday that optical fibers are amazing. Don't think optical fibers are not. They are amazing. Okay? They are really, really good. If you have internet which is connected through cables underneath your ground and they come and they install it, that's how your streamers, these internet streamers use. It's internet connected underground, a lot of them, to have stability for them to be sure that they can go on YouTube streaming nicely. So they use optical fibers. Okay? They use optical fibers. I once had it installed. It's fast Wi-Fi. You can use anything, stream, download, everything. Okay? What reason? Okay, used in optical fibers, say for high speed data transmission. For high speed data transmission. Why do we use infrared? Because all the others can also do it. Why does it have to be infrared? Because all the others, all of them move at the same speed. All of them move at the speed of light. So why does it have to be infrared or this? Reason, because it can go through total internal reflection. Okay, you have this infrared and stuff. They can go through total internal reflection. When you study optical fibers, you're going to find out that they do what we call total internal reflection, which means that's how light moves through an optical fiber. We'll talk about total internal reflection in the next thing after we do refraction, okay? We'll do refraction of light, then we'll understand what is total internal reflection. By the way, sir, why do you keep doing things like ray diagrams, electromagnetic spectrum, the waves, all this theory? Why haven't we seen a formula? I know what I'm doing, man. You are not going to see a formula until we are happily done with all the theory. I'm going to teach you to do calculations. Calculations are the easiest thing ever. Anyone who does physics with me should be able to pass all calculation questions without even dropping a drop of sweat. Okay? It will be an offense to me if any of you struggle with a calculation in physics. I will be totally disappointed. Are we together? Because there's the nice way of doing it that I always teach you. I'll teach you again for all those who are new. Okay? Yes. Would rather not get theory, not a calculation. Calculation? Man, we are going to get 100 on that. So let's make sure our theory is good because our calculation is easy. Calculation questions. Now let's do, so this is the last thing now, the part number 5. Then I can say, yes, you're done a little bit. We can say that. Done with electromagnetic spectrum. Say digital versus analog signals. Digital versus analog signals. Digital versus analog signals. Can you all see my screen? Class, can you all see my screen? Right, let's just wrap it up. Digital versus analog signals. Studying signals, and you want to see, right, let's just write here to say digital signals are better than analog signals because one, they are less affected by noise. Okay? Then two, write for me this. They can travel faster. Then three, write for me, three. They support error checking. They support error checking. Digital signals, they support error checking. Are we together? Let's just put the fourth one. They can also travel further. They can also travel further. Can you write these important points that I've just given you? Okay? Have you written them? Write for me this, please. Write for me this, please. Are we together? If you want to know a signal is a voltage or current that varies with time. A voltage or signal where its value can go up or down. That's a signal. Okay? Are we together? Or an electromagnetic wave that continuously varies with time. Okay? That varies with time. Carrying information. Carrying information. That's a signal. Okay? So it's a variable. It varies. Are we together? Hello? Yes. So anything that varies, I hope you know. Now, we want to know, I want to give, all you need to know is, all you have to know is one versus the other in terms of digital signals versus analog. So that's where I will focus on. But when we say we have analog signal, just write for me this. Analog signal can, say, continuously varies. Yes, it continuously varies. Yes. Yes. Oh, it can be a voltage. So, in other words, basically, Roderick, when we say a signal can be a voltage, we are just saying, by the way, voltage in electricity, I haven't really explained this, but voltage in electricity is just energy. It's energy. So when we say we have a signal, we have some form of energy. Okay? And this energy, the values, if the values of energy are going up and down, changing like that, then we say we have a signal. Do you understand? Do you know that? Do you know that an electric? Do you know that you are right now? For you to think right now, you are using some voltage. Do you know that coordination and response? We said it last time. We said, how does the nervous system work? It uses what? Nervous impulses. What are they? They're signals, right? So there's something. So and they're used to carry information. So ones and zeros and zeros and ones and ones and zeros. So those information, that signal, that with zeros and ones and or up and down and values, it's actually information. Your brain knows how to interpret it. So a message that comes from your hand to say, that comes from the receptors in your hand to say, I'm bending, lift the hand. It's a signal. It's an electrical impulse. It's a voltage that either goes up or down. Some voltage, you feel it, that voltage or up and down feeling there is a signal passing through your body, which is a message. You understand? So messages move as values, as energies. They move as some energies there. So when we are talking about signals, we are saying, how does communication move? So either we can have something called an analog signal, which is, it's traditional. Analog signals are old. They are not used nowadays much because they try to copy after the original sound. So what, or the original ray, or whatever the original thing, the original signal. And because of that, they are going to have many values. They take any value. When we say something is analog, it has a wide range of values. Are we together? So analog signal continuously varies, taking any value. It takes any value. Okay? A digital signal, it also varies, but a digital signal can only have one of two discrete values. It can only have a 0 or a 1. Are we together? Discrete states. And say discrete values. It's either a high or a low. Digital signals will either be a high or a low. So message goes as either a high or a low. And it moves faster. It goes further. It's less affected by noise, which what we call noise in communication, it means an unwanted sound. Are we together? An unwanted sound. You know that old microphones get all the noise you'll be hearing on the mic. They're getting the chirping of the bed. They're getting those are noise. That's noise. That's interference. That's a sound that we didn't want. But if we're using digital signals, then it's less affected by noise. It can travel further. It can travel faster. It supports error checking. All these things. Are we together? I wrote them here. Can you see? You should know. It's just something you should know. That's why I'm just making sure you know all the points that the syllabus wants you to know. Are we together? All right. Now let's just put it as a table. The things that we the quality, the noise, the speed, we compare for this. So we are going to say feature, then you're going to say how is it on an analog signal, right? For me, analog signal. Then how is this feature on a digital signal? Let me explain to you. Do you people know what we call a mixer? Do you people know how to call a mixer? Okay, let me not try to explain. But okay, it's just something that is used to balance the sound. You have a person playing a piano, you have another person who is singing, you have another person who is playing drums, you have another person who is playing a saxophone, you have another person who is doing something. All these people are producing sound. Now, you want the volumes to be controlled and balanced. You can use a digital mixer or an analog one. An analog one, okay, digital mixer shows you values, it's easier. But anyway, if we talk about signals in sound, just say this. Digital means it can be a 0 or 1 only. Analog, it means that signal can take any value. Are we together? Now, let's see here. So we're going to say the quality of sound when you are using a digital signal. The quality of sound on an analog signal. If it's an analog signal that is carrying the sound from place to place, then the quality is going to decrease with distance. It's called attenuation. It decreases with distance. Okay? You're going to be studying this and studying what we call decibels. We'll be studying the strength of your wave. Now, but when it moves as a digital signal, then it's going to maintain the quality. It maintains quality. Are we together? So on a digital signal, does your wave get affected? When you have a wave moving as a digital signal, is it going to be affected in communications? No, the quality will stay the same. Are we together? It won't be affected much. The quality is going to be maintained. What about noise? Unwanted sounds. We are doing communications, right? Oh, there's noise. Here, it is affected. It is affected by interference. So there's a lot of noise. It is affected by interference. Here, not easily affected. Not easily affected. Your sound can move nicely. Now, what about the speed? The speed. Which one is faster? Of course, this one is faster. And this one is slower. And what about their types? What is the type when you look at a digital signal? What is the type and what is the type of an analog signal? An analog, the type, what is the type of an analog signal? We said it is any value. So we say it is continuous. Here it is zeros and ones. Anyway, this is the last. Oh, I should have put it up high so that people can see when on the recording. Put it like this. Can you all put it like this? Zeros and ones. For the other one, then you can have it like that. Are we together? Right. Next up, obviously, is past paper questions on these things. We'll cover that. Our past paper questions, we'll go through it and I'll see how you're all doing. So we'll do that in our next lesson tomorrow. We'll do past papers from these things. Okay? Good. Let me stop the recording. All right. Now I need to do those past paper questions we had for bio. Let me text those students who do bio to join. Give me 1 sec. Let me see this register for physics. I'm interested in seeing the people who were there for physics. Give me a second. Yes, yes, Roderick. No, class is not over. Okay, you mean you said during what is it? During communications, do we convert from analog to digital, from digital to analog? Well, I don't know. That is definitely not something that people should know right now. The secret with life, let me just shock you right now. Isn't right now you study chemistry, right? Right. When you study chemistry, what do you know? What are you told? You are told that an atom, no, the shape of an atom, people don't argue, okay? It's going to be the same forever. But you guys are told that electrons are here. Let me show you. The shape of an atom is okay. To say the nucleus is at the center, then you have the outside, okay. Now, the biggest question that people have is, okay, remember that we do not study the wall of an atom. There is nothing called the wall of an atom. So in chemistry and in physics, we don't want to know about this thing here. It's known in bio, the wall of a cell. But when we do at the atom, we don't do about the wall of an atom. We do about where electrons are. So we know that most of the atom is empty space. We don't care about, does it have a wall? What does the wall look like? We don't care. But we learn that electrons are here. There are 2 in the first shell. Then after that there are 8. This is what you learn, right? What you're going to see is that when you're going to get to A level, they'll say, actually, this is false. Say, what? This is false? Yes. And it used to bother me because I used to ask the A level teacher to say, sir, why have we started to learn something completely different? Is that thing false? And they couldn't really answer because back then we didn't have things like Ch.3 to ask. We just had to ask our teachers and stuff. When I then got to university and I was now doing this again in whatever I was doing at university, I started to research now to say, how come at IG they told me this? And now they were showing me that we have orbitals that look like this. And electrons are not here even. They are somewhere in this space, somewhere around this area. And another orbital can be like this here. Another orbital like this. Then we have another orbital that goes inside and outside like this. To say, how come? So let me tell you something about learning and science and all this. You start somewhere, then they keep adding. So it's not that this is wrong. No. They don't teach you something, then they say, now throw it away. We're now no. This is correct, but it's only correct for hydrogen and helium when it comes to doing hard things, real hard things, and explaining what they call spectra of light, the line spectrum, stuff like that. So they now have to do this one, which is called the quantum mechanical model. If I was teaching you A-level chem, I would explain it nicely to you. But once you get to 3, using this one will make you be, let's just say, I don't want to say crippled, but it will hold you back because you can't really do hard things when you are using this type of an atom where electrons are in nice circles, nice circles around the nucleus. No, my friend. Electrons are not found somewhere so easy. Electrons are in regions. They move around, but you can predict where to find them. You can predict where you can go. You can't go here. There will be no electron. There will never be an electron here. But if you go into these regions, you can find it. Are we together now? So what I'm saying is, as you are going to be going deeper, Roderick, everything will be, you'll be now doing more and more and more until finally when you have done masters or PhD, we will now say, Roderick, now you know everything that human beings know about this subject. There is nothing new to learn. We are actually now waiting for you to do research and tell us more. Do you understand? People who have done PhD have finished all books. They'll be knowing everything. Now they'll be doing what is called research for them to be called professors. When they do PhD, they are called doctors. To say, doc, you now know everything. When they are now called professors, it means they have actually added to what we know. They have done research and they've added. Anyway, so Roderick, what you are needed to know, what they expect you to know right now for IGCSE stage, if you want to do telecommunications engineering, that's good. It's not easy, okay? To understand how a cell phone works is a very, very hard thing. It's one of those chapters that I really, really didn't like when I did A-level physics. But it is also okay. You can study it, Roderick. You will now start to be able to explain to us, because I don't know, you'll be able to explain to us about these changes between digital and analog, okay? What happens at which stage and whatever. Okay, Roderick? Right now we want you to know these. They're going to be asked in the exam in 5 months' time. You'll be holding a pen and you'll be given a paper by an invigilator. And they'll say start. And there'll be this information. So make sure you know this one. Right. Give me 1 second. I need to call Michelle now to start bio. Okay, welcome, Michelle. I see you. Now, let me open the bio papers. And we get logged in to do those Punnett squares. Do you still remember the Punnett squares we did yesterday, everybody? Do you remember the 4 types? Why are you quiet? Have you forgotten them? Class, do you remember the Punnett squares we did yesterday? The 4 types of Punnett squares. Right. Let's see if you remember. So they're gonna tell us information here, and then we're gonna answer. So wait, let me just